Hello, everybody. My name is Vinicius Rocha. So the title of the seminar today is First Principle for Calculating Photodynamic Therapy Spectroscopy Properties. Here we have the original work. Can you see my set? The model you
Yes.
see?
Yes, it's okay.
Here we have the original work. Well, the main motivation of this study is the photodynamics therapy that consists of an optical singlet excitation and the subsequent singlet-triplet intersystem crossing. We have here a molecule that we call the photosensitizer. So we put radiation there and he left to a excited state. So here, the molecule can come back for another excited state by a process that we call internal conversion with the same multiplicity, or they can through another state that different multiplicity by a process that we call intersystem crossing. The intersystem crossing, in principle, it's forbidden. However, the spin-orbit coupling between these two states can be large enough to make it possible. The mechanism is the vertical excitation of the photosensitizer of a singlet to another singlet state, and intersystem crossing between the singlet state to a triplet state. And in the triplet states, the molecule interact with the oxygen. The oxygen is naturally a triplet state. So when they interacting, the oxygen, we can generate singlet oxygen that's very reactive. So the idea is put the photosensitizer in a tumor cells, for example. So put radiation there, the mechanism will be occur, will generate the singlet oxygen, and he leads a cell death. So what we want is to study the mechanisms of the excited states dynamics here. So we want to solve a problem of many electrons using first principles. That is, instead of using models, we'll use approximation and use Schrödinger's quantum mechanics. For that, we use the density functional theory. The idea of this theory is, instead of using the wave functions as the main variable, we will use electronic density, an easy amount to calculate and that has dependence of only three special variables. So with this approximation, we arrive at a Schrödinger type equation that we call Chem equations. So we have a self-consistent problem to solve that I will not go into many details. In its the potential called the effective potential of the equation, we have the term of exchange and correlation. That's a correction we do to the residual kinetic energy of the electrons. The exact expression of the functional of the exchange and correlation energy is not known. So it's necessary to determine a good approximation for the exchange and correlation term, which is the most difficult physical interpretation term of the density functional theory. So for calculate the rates of the electronic transitions, we will use the DFT theory, and the general expression for the rate constant of the non-radiative electronic transitions is that is derived by Plotnikov-Robinson. So Y here is the initial electronic state, F is the final electronic state, N is a vibrational level of the final state, gamma is the relaxation wind of the vibronic level F, and delta is the energy difference between the initial and the final vibronic states. And this V here is the matrix element of the perturbation operator. When assume that gamma depends only weakly on the vibrational level N, we can do that approximation and we have the expression here. So we have what we have know is that V here. Well, for the internal conversion transitions, that is a transition from the for states with Chem multiplicity, we have this expression here, where V in the framework of the adiabatic and Frank-Condon approximation, we can write V of here, like here, where T is the kinetic energy operator of the electrons, Ni is the nuclear index, M is the mass of nucleus, and these matrix elements here, the last one here is the non-adiabatic coupling matrix elements between the state C and F. And this one here is the non-adiabatic coupled elements between the level 0, the ground states, and the state 10. So for the intersystem crossing transitions, we can write the rate like this. The spin orbit coupling is the perturbation operator of the intersystem crossing process. The spin orbit coupling matrix elements depend only of the space and spin coordinates of the electrons, but not the nuclear ones. And this Y here,
okay, 2 minutes,
is the Hwang-Hughes factors. So we can calculate the spin orbit coupling matrix elements by a Breit-Pauli approximation. Now here we have the molecules studied in this work. The molecules were chosen for many reasons. The PM567 here, for example, has a very large fluorescence quantum fields and is often used in laser device. Pseudolen has a very small fluorescence quantum fields and a large intersystem crossing rates, and it's therefore used in photodynamics therapy applications. The free-base porphyrin is still used for photodynamics therapy, and ALK3 and ERPPY3 is often used in OLED devices. So we need the matrix elements of the intersystem crossing and the internal conversion, the Hwang-Hughes factors, the energy, the difference energy between the two states, the gamma, F, and the vibration frequency of these molecules. So here we have the levels of theory that we use for the authors. Here they specify the exchange coherential potentials and the base functional for the orbitals. So here we have the results for the PM567. We have the molecular structure optimized here, and the energy level diagram, including the computed values of the radiative and the non-radiative constants. Here we have I'm finished. Here we have the results for psoralen, denominating the activated channel of the S1 state is via the intersystem crossing 1 here, because of the strong spin orbital coupling interactions between S1 and T1. Here we have the results for the circlants for B and AOC. They don't can choose values for the intersystem crossing for these molecules. Here we have the free base porphyrin. They calculate rate constant for the non-radiative transitions of intersystem crossing and internal conversions are underestimated. Here they said by the experimental results. We have the results for the ALK3 and the PPY3. And here we have the results for the naphthalene, anthracene, tetracene, and pentacene. Here we just done these results for compare with the experimental results that was known. So the conclusions, the radiative process dominates for PM567 and NOC. The non-radiative intersystem crossing process dominates for psoralen and EPPY3, whereas the non-radiative internal conversion process dominates for the tetraoxycirclan. The accuracy of the calculated internal conversion and intersystem crossing rates constant depends strongly on the accuracy of the calculated excitation energies of the excited singlet and triplet states, and the present approach makes it possible to estimate rate constants for non-radiative transitions for organic and organometallic compounds within the Frank-Condon and adiabatic approximation by using calculated values of the matrix elements of the spin-orbital coupling interaction and the non-adiabatic coupling interaction. That's it.
Ok, muito obrigado.
Obrigado.